Thank you. Very good morning, ladies and gentlemen. I'm happy to see you all here. The chocolates are waiting for you for great questions. So do not forget about that. Please collect the questions along the story. We have two tutorials today, broadly in the area of natural language processing, terminology recognition, multilinguality, building aligned multilingual thesaurus. There will be a strong practical part run by my colleague Dmytro Chaplinsky. And I will be giving you a sort of an introductory overview over the domain. So this first tutorial is about the research frontiers in automated terminology recognition. As far as nobody is going to present me, I will do myself. So I'm a knowledge engineer having quite some years of research and development experience in semantic web and semantic technologies, including natural language processing, automated term recognition, distributed artificial intelligence, building on agent-based systems, knowledge graph and ontology engineering, also from natural language texts. Currently, I'm a professor of semantic technologies here in UCU at the Department of Computer Science and Information Technologies. I'm also directing a PhD program here, and therefore I'm sort of responsible for this summer school, which is proposed by our first-year PhD students. More information about myself could be seen over there, and this is the station graph during the last 24 years. So I have some papers, and luckily I do have some citations. And this is about the sort of impact. I'm a honoris causa professor at Kherson State University in Ukraine. I've been a visiting professor, research fellow at various European locations, including leading universities in Germany, England, Spain, France, Austria. I'm the founder of Intelligent Systems Research Group at Zaporizhzhia National University, which is in my previous life. And I served as a research consultant for industries, quite big companies like Cadence Design Systems Incorporated, like Group BVT, and so on. I'm also serving for different programs in the European Commission as an external expert. So this is it. Sorry for this MBA-like presentation, but, well, it's a sort of a necessity to let you know who is talking today. So my plan for this tutorial for today is to answer these three questions broadly. The first is about the difficulties, about the challenges. Why is it difficult to recognize terms automatically? Then, what has been happening around during some time, starting at the beginning of this millennium, and what was the evolution of the state of the art in automated term recognition? And finally, what is in front of us beyond the frontiers in the future? I will be giving some indications and some hints on that. I'm not pretending to make it complete because of the limited time for the tutorial. Finally, I will be happy to answer your questions and be able to give the answers. Let us start with the challenges. I will tell you what is a term. To be more correct, I will not tell you what is a term. I will tell you instead what is automated term recognition, and I will emphasize why the stuff is that difficult. This is the definition I grabbed from Merriam-Webster dictionary, by the way. The most straightforward venue if you don't know how to denote a thing. So it says the term is a word or expression that has a precise meaning in some uses or is peculiar to a science, art, profession, or subject? Quite a vague formulation for a mathematician. Yeah. Yeah, it's a phrase, our expression, an expression. Yeah, there's a quite a big bunch of questions arising if you start analyzing this stuff. And I will guide you through this analysis right now. So, which parts are terms here in this definition? I highlighted something and bolded something. Is a word a term or expression or a meaning with a qualifier precise, a use, science, art, profession, a subject? Just to make it a little bit easier, I extracted some phrases or some expressions. These are word, expression, meaning, precise meaning, uses, some use, science, art, profession, subject. I'm also looking at has. I'm also looking at speculative. Are those terms? Indeed. Why could one think those are terms? Do they adhere to the definition aside? Any opinions on that? I think we cannot do that because both the list and the definition are vague and implicit, isn't it? Yep. Why A is not a term? Yeah, yeah. Well, which is not explicit. We just call our intuition to the front line and try to do something. Let's try to elaborate it a little bit more and change the approach. Let us look at the sense, at the semantics, concentrating on the precise meaning in the definition, which means that we are intending to make the definition a little bit more formal and a little bit more explicit. For example, by providing a UML sort of class diagram. So what do we have here? We have a term as a central entity here, and we analyze the features, the attributes, or the properties of the term. We can see that it could be either a word or an expression, which are superclasses for a term. We could see that it is somehow associated with the meaning, which has a qualifier precise, could be Boolean, could be whatever. A meaning is associated with the context of use, and the term is peculiar to a domain, which is a superclass for subject, science, art, and profession. Anything I missed here? You'll be surprised, a lot of things. The first is the answer to a question, is an expression term indeed a term based on this definition? What do you think? What does your intuition hint you? Is a term as an expression, as a short string, a term? Yeah. It does not. It does not. It does have a precise meaning, at least up to the precision of the UML class diagram. So I have more questions here. Which domain is term peculiar to? Can you Automatic term recognition. This is it. Nothing more. Nothing else. Nothing more precise.
All science.
All science. All arts.
Arts, yeah.
We even had a keynote at one of the conferences, which was named in sort of important terms, and then it was about an art. So one more good question here is, is peculiar to a term. It's also a sort of an expression here, a string. Do you think it's a term? Why yes and why not?
Precise meaning, you mean? This.
No, peculiar to. This one.
Peculiar.
Peculiar to.
Certainly not.
Why not?
What is peculiar or why is it? It has no precise meaning. It doesn't refer. It's very subjective.
So it does not have a concept semantics at the background. Yeah, your opinion?
Well, I would actually say yes if it's meaning what it means on there, right? Like if it's very specific.
Yeah,
I would say if you separate it, no.
Here.
If you put it together, yes, because it means it's like code operator.
Well, it is a sort of a word because there are no spaces in between the parts, right?
Yeah, so then
it's a sort of an expression containing just one word. I'm just matching it to the definition. It has a sort of a meaning because it connects a term to a domain. No, what are the uses? That could be a problem. How it is related to a science and art or profession or a subject. That could be a problem as well. So I have quite a broad list of questions in this context, and therefore I would suggest that we keep on suffering that way. Let's look at the first thing. A term is a word or a term is an expression. What is a word? Is it a term or not a term? What kind of expression? Is it a mathematical expression? Is it a logical expression? Is it just an informal expression? Is it a normative expression? What is the norm? And so on and so forth. A term has meaning with a qualifier precise in the context of use. And here I do wonder what is meaning. What does precise mean? Is it just Boolean? Or it's fuzzy? Or it could be measured in a different way? How broad the context of use is? In that sense, is common sense a domain? So the things we know commonly, like there is a gravity here. This is the part of common sense. Is it a domain? Could terms be common sense terms? And many more questions. So let's return back and make one more iteration. Is an expression term a term by definition? Now it's a little bit more precise, but well, as for me, it is not yet clear in that. So let's go further. I would better ask the same question about a term being a term in a different way. Focusing on the definition we have used to qualify if it belongs to terms and does not belong. Is the definition we have seen so far sufficiently precise in its meaning? That's a little bit more constructive question. So if we manage to answer this, I believe we could manage to go further in distinguishing between terms and not terms. There are many more things to think about in the context. For example, if we look at the expressions listed here, Golden Gate Bridge in the domain of infrastructure, Donald Trump in the domain of state governance, Tequila Sunrise in movies, sportswear, cocktails, music, many domains, many different meanings, by the way, for Tequila Sunrise. So these points us to several pragmatic contexts, which will be discussed shortly in the next slide. So if we look here, we will qualify these expressions perhaps like named entities, which label something, which are instances of what? So a Golden Gate Bridge is a label for a well-known bridge. Objects. Instances of classes. Yeah. Donald Trump is badly known instance of a POTUS. Tequila Sunrise. That's a little bit more complicated, and I will show you different shades of this meaning just in the next slide. What? Okay, thank you. Let us look at an expression butterfly in terms of its adherence to different pragmatic contexts and the ambiguity of this expression considered as a candidate for a term. Could you please define butterfly? An insect, yeah. Any more opinions? Dissenting? I will give you several examples. Just take a look. This is a game, an Oriental game with the name butterfly, because the shape of this step recalls the butterfly. And this is a swimming technique, which is not an insect. And this is a goalkeeping technique, which is not in swimming.
Yep, but all these are mimicked after the primary term butterfly as an insect.
I would be happy to formalize the process of mimicking. So, well, at least, well, within the context of automated term recognition, we're forced to look at the landscape quite superficially, because we are not supplied with the underlying meanings of those islands or points on the landscape, and we cannot use it. So we may use just the things which are available in the text. And if text says a butterfly and speaks about a swimming technique, butterfly means that it's a swimming technique. So, or goalkeeping technique, or, oops, or a film, by the way. Please pick any of a dozen, even more than a dozen. So, which are named entities, by the way. And indeed, yet not mentioning the obvious, insects in different shapes and forms. So a good question here, is butterfly a term by the definition we have used already?
Well, probably not without a context, because
Without a
right now
pragmatic context, yeah?
yeah.
Okay.
Yeah. So it's homonym, so there are lots of meanings that can be associated with it in specific examples.
Absolutely, thank you. Yep.
So if that's true, I'm confused why that's not also true of the term, if it has many different meanings, or it's always one meaning if different instances versus many different meanings in different contexts.
I'm now talking about a term as a term.
Yeah.
Could you qualify several meanings of the term?
I think you're right. I'm thinking of specific instances because it's always, yeah, okay. Because yeah, it would be the term butterfly. It's always one. You're right. Never mind.
Yeah, no, but you are quite right. Perhaps the example is not that easy to analyze because, for example, if you are saying in terms of uncertain terms, then there would be some two different shades and sense of the meaning within the same phrase. So let us go further. So far, I mean, all those mental exercises we have undertaken that far were undertaken just to convince you that it's hard to denote a term precisely. The definition we used was imprecise, was vague and implicit, in fact. And this is why it's even harder to recognize terms. However, even kids are quite keen in recognizing terms, in learning terms, also from texts. What I did to somehow justify this claim, I prompted ChatGPT, contextualized it as a primary school teacher, asking to generate a text for primary school pupils on Golden Gate Bridge, to explain them in popular terms, what is the Golden Gate Bridge. This is the text generated by ChatGPT free of charge. Thank you very much. And that is the prompt. You are a primary school teacher. Please generate a text about the Golden Gate Bridge for your class. So kids are quite keen because they're still going the semantic way, following these steps. Yeah, you had a question? I just wanted to add that it is natural text understanding. I mean, this pipeline for kids is natural text understanding, isn't it? And they do it step by step. I will try to visualize you how they do that, step by step. So let us start with the most simple thing, which they have been taught by their teacher. They read the text, and then they intuitively extract expressions such as Golden Gate Bridge, famous bridges, is found in United States, city of San Francisco, California, Golden Gate Strait, Porter, San Diego, and so on. Then they start analyzing these expressions by mapping them to their knowledge. For example, they do see that a Golden Gate Bridge is an instance of a bridge. A Golden Gate Strait is an instance of a strait. California is the instance of a region, and so on, so on, so on, so on. Further, they denote properties which come up or pop up in the analysis, like an instance of famous, color equals to red, orange, found in, and so on. And if they cannot do something in a smaller context, they just ask questions. You just say, hey, teacher, is San Francisco in California? Or what are the United States? Further, they try to disambiguate things if there is a possibility to see it ambiguous. For example, a bridge could be a part of an infrastructure or a card game. So they have to decide. Can you guess how they decide? They do. They do. They do. I mean, at their age, 50 years ago, we didn't know, but now they do. Yeah.
Context.
Say it again.
Context.
Context. Yeah. They put it in the context, which is within their knowledge map, and they analyze the properties. So they look at the concept of a bridge in terms of being a card game and analyze, try to prove or disprove these hypotheses by analyzing the properties. It's found in a city which does not really resemble a card game. It crosses over a strait, which is indeed not a card game. Therefore, they consider this hypothesis of bridge being a subclass of a card game as a fake hypothesis and prove the infrastructure hypothesis in the same way. So this allows them to contextualize and perhaps choose the pragmatic context of this or that expression, which is a term candidate. So finally, after contextualization, after being certain that a bridge is part of an infrastructure, they categorize the things they have marked up in the text, like concepts, bolded, like named entity, italics, like feature in green, like relationship in violet, and so on. And after doing that, they just add this new piece of knowledge to their theory of the world. This is what kids do. Why not computers? Some people think that in the era of generative AI, they will soon lose their professions. Even kids will not lose their profession for quite some time, because generative AI cannot still outsmart even kids in this. Yes.
Is it semiotics, like meaning? The computer doesn't understand the meaning of the words?
Yes, yes, this is it. This is it. And this is how machines recognized him, which is a bird's eye view, of course. I'm not going into details for now. So they take in texts in a natural language, English, Ukrainian, some other Mandarin, and then they pre-process those texts. I will omit the details of pre-processing at the moment. And then they recognize candidate terms using this or that approach, sort of magic. And then they score and rank these term candidates by using the notions of a termhood and a unihood. Termhood measures how strongly a candidate word or phrase is related to a specific domain. So is a domain-specific term, like a bridge in infrastructure. A unihood measures how strongly words in a multi-word expression belong together, forming a stable unit. This could be done by picking the occurrences and counting the frequencies. And the frequencies would be arguments in favor or not in favor of that decision. So after the candidates are ranked and scored, the top candidates, which are with the confidences or rankings above the threshold, are left in the set of extracted or recognized terms, and the rest is just junked. So we arrive at the ranked list of terms. I also asked ChatGPT to recognize terms in the text that it has just generated for primary school pupils. This is what kids did, as we already discussed. And this is what ChatGPT did. So it was a neural way. It was zero-shot prompting. It was the same text which has been suggested by ChatGPT contextualized as a primary school teacher. And the result is bolded. So what can we see if we look at the result? That's, so to say, miserable compared to the kids. And if we look in more details, we'll see that ChatGPT was good in recognizing named entities like Golden Gate Bridge, like United States, San Francisco, California, Golden Gate Strait, and was miserably bad in recognizing the rest. For example, it highlighted famous as a term and did not highlight bridge as a term. I'm quite sure that careful prompt engineering and few shot approach might improve the situation. But kids do not do multiple shot. What I have
they ask parents and everybody.
or teachers. Or teachers. Yeah. What is the United States? What is the hell United States? And get this. Okay. I have to, just to be to be fair, I have to recall that kids might have been taught conceptual modeling and knowledge representation to create their mind maps and to analyze the intrinsic tacit formalities in the natural language text. This is quite a skill. And of course, kids are not taught how to do that. Students are taught. So now one more good question is about where is a term in a proto-language? Well, it's clear that a term is a part of a language. Question is, where is it? What part of a language is occupied by terminologies? So this is a citation from the quantitative analysis of the dynamics and structure of terminologies. And as one can see here, terminology is in its major part within the vocabulary of language, which is a little bit more constrained than general vocabulary. And there is a sort of a slight overlapping between terminology and a general vocabulary. On the other hand, terminologies are, extend out of the vocabulary and overlap with the formal sign systems, like expressions in a formal language. For example, in the knowledge specification language. So this stuff has explicit meaning. This stuff does not have explicit meaning, and the vocabulary, mainly the general vocabulary, is characterized by being ambiguous, irregular in meanings, and not really precise in terms of being formal and explicit. So one more paper proposed a sort of a categorization or typology of terms. They are speaking about different types of terms along two aspects, like lexicon specificity and domain specificity. So the more specific, both for lexicon and for domain, are domain-specific terms, like here. And the non-terms are the less specific in both aspects. So there are intermediate things and intermediate categories, like out-of-domain terms. They are more specific in lexicon, but less specific in domain. Yep.
Specificity is kind of like, to be in the top quadrant, does it need to be something like, you said the word topology, that has a very distinct mathematical definition, like it has, you could code what it means. Does that make sense? Does it need to be that specific, or could it be whatever the name of a bone in your finger is? Does that make sense?
Domain specificity means that a domain could be broader or narrower, or it couldn't be a sort of a domain, but it could rather be considered like a common sense, which is the broadest, like a universe of discourse, if you wish. So the less specific in terms of a domain means the broader span. And the more specific means that it's more explicit in its meaning. So different pragmatic contexts of an expression indicate about less domain specificity. Yep, yep. Similar thing about the lexicon. There are just two independent aspects to analyze, proposed by the authors of this paper to suggest these four categories of terms and not terms. So, based on that, is butterfly a term? Which sort of? Domain specific?
Out of domain.
Out of domain? Common term? Yep. Out of domain. Why? Any arguments on that?
It like means a specific thing, and that there's only certain things that could, if I understand this spectrum correctly, it's like only certain things could be butterflies. Like it has that specificity, but it depends on what domain you're talking about, what it actually means.
But when you see a butterfly without a pragmatic context, you may think that it might belong to several specific domains, like goalkeeping technique, swimming technique, game, like insects. So if you still allow this expression to belong to all of this, then is it a term or not a term? And if a term, which kind of? Is it? Not a term. Well, I'm not sure myself. So you have to make a fine-grained typology to be able to qualify and categorize expressions as terms within this category. So let us now look at the state of the art. So far, we just looked at why it was challenging. Let us now look at how people tried to attack the challenge. What is the state of the art in the automated term recognition? I will tell you about the typology of the methods of the attempts to attack the problem. I will show you a couple of leaderboards, and I will finalize this part by identifying the list of research gaps. So this is the evolution of automated term recognition in terms of the number of papers per year. The source for this diagram has been the Scopus database. So those sources are quite reliable. So what do we see here? We see that things started 20 or 30, or I would say 40 years ago. There are not a lot of publications. And then finally, we've got to a peak of inflated expectations if you map it to a Gartner curve, for instance. So which started in 2017. And then we came up to the culmination here at 2020. And that was the last ATR contest on this actor data set, the European adventure. And then we have taken a bumpy slope of disillusionment, again compared to Gartner's terms. So you will be wondering, why the slope was bumpy and why it came to a disillusionment curve. I will show you the examples. I will, well, substantiate this observation. So if we also look at, here we do see the rise of the neural. And it is somewhere in between 2022 and 2023. What was the markup event? General pre-trained transformers, transformer architectures, which led us to the rise, large language models, which led us to the rise of the neural in 2022 on, starting at birth. Okay. Let us compare it with the named entity recognition curve. As the same source, but as you see, we have about 6 times more papers for named entity recognition than for general terminology recognition. And it peaks in a similar way like the ATR curve, but 3 years later. And of course, the data for 2025 is not yet complete, so therefore the decline. Don't pay attention to this decline. And by the way, the slides will be available if you pay. So let us now look at the evolution of different families of methods. Well, the adventure started at around 1980 with the linguistic string project somewhere in the US. And it gave birth to the linguistic family of methods. Then there was the inventor of the statistical approach, which has been based on analyzing the frequency and syntactic patterns. What is, does this or that expression map into a syntactic pattern, and how frequently it does? And then at around 1994 and on, one more family of methods, graph-based methods, have been invented, which were using the so-called co-occurrence graphs, where the candidate terms, I mean the textual expressions, are the vertices in a graph, and the edges were weighted by the frequencies of co-occurrence. Then machine learning-based methods have been proposed at the very end of the previous millennium, and mainly they've been using classical machine learning methods for solving the classification task, a term or not a term, sort of a binary classification, or which kind of a term. Then there was the rise of deep learning-based methods, which were using multitask learning, word embeddings, and those methods were trained on a domain-specific corpora. And finally, and this is the explanation for the rise of the neural, language model-based methods. The pioneering paper has been written in 2020, which used BERT embeddings, domain-specific fine-tuning. And there were some deviations from this pioneering paper, like SciBERT or BioBERT for different domains, for the common, for general scientific domain or for the biology domain. So what is interesting in the analysis of all those families of methods, the majority of the most successful methods at their culmination points were hybrid, which means that they combined different techniques taken from different families. For example, linguistic and statistical together. For example, graph-based and linguistic together. I will show you a little bit more detail in one of the upcoming slides. Like here. This is the topology, in fact. We have rule-based methods, which include linguistic and statistical, and also hybrid linguistic plus statistical, for example, C or NC value method proposed in 2000. The graph-based methods looked at co-occurrence graphs I mentioned already, and there are also hybrid graph-based methods, which first take linguistic plus statistical for pre-processing, for initial ranking, and then building the co-occurrence graph based on the ranking table. So machine learning based are the methods which were classifiers. Those methods also were hybrid, including linguistic and statistical information about the term candidates as the features for the network. For example, such features as part of speech tags, TF-IDF frequency, semantic information, mutual information, left-right entropy, which is the predecessor of embedding analysis, and so on. DL-based is also a classification approach, which uses embeddings mainly at sentence level or at document level. And it also could be hybrid using both classification and embeddings in one bundle, like Amajdian's paper in 2016. So good thing is that the accuracy of deep learning-based methods has been close to expert performance. A disadvantage was that they required significant resources for domain-based training. So you have to collect a domain corpora, you have to label the corpora, and then train the method to recognize terms in this domain. And finally, language model-based, which to exploit pre-trained models, which are domain neutral but are not very successful in recognizing terms, then the model is fine-tuned for a particular domain. Prompt engineering is also exploited, like we mentioned when we analyzed zero shot and few shot for ChatGPT over the Golden Gate Bridge text. And LLM is also used as a judge here. Those are the examples of language models which have been used in the published work on automated term recognition using language model-based approaches. Later in this tutorial, I will focus on those two because I'm a little bit constrained in time, and leave the rest, or not really the rest, but some indications of the rest to Dmitro, who will be giving the next tutorial with the emphasis on the practice. Let's look at rule-based linguistic methods. The idea of this family of methods is that terms follow grammatical patterns at sentence level, and terms are noun phrases. So is peculiar to is not a term because it's not a noun phrase. This is language dependent, of course, because you can do part of speech tagging, or you can't do part of speech tagging, for instance, independently of a language. It's different for English and German, for instance, or it's different for German and Ukrainian. Yep, you have a question? Or you just have to use a separate tagger for a different language. Because the rules of tagging change. And the recognition of nouns and adjectives and the rest of the parts of the speech is different and changes from language to language. Yeah. So So the grammars are different for different languages, and therefore parts of speech are different. So the generic pipeline comprises cleaning, chunking, tokenization, lemmatization as an option, part of speech tagging, extracting linguistic patterns, and linguistic filtering. So this is for post tagging, based on one sentence from our Golden Gate Bridge example. So this is the sentence. The Golden Gate Bridge is one of the most famous bridges in the world. So we analyze using a post tagger, and each unigram, each word gets its label. Like this is an article, this is an adjective, this is a noun, this is a noun, this is a verb, this is a numeral, this is a preposition, and so on, so on, so on. And then we do chunking by selecting the groups of as long as possible noun phrases. For example, Golden Gate Bridge. It's one of the longest or most famous bridges in the world. World is just a noun phrase which contains just one word. It's a unigram. So we focus or prioritize the longer noun phrases. And then we apply some linguistic patterns, like part of speech sequences, which are normally specified as rules. The rules might say that a noun, a phrase containing just a noun could be a term candidate, or a phrase which starts with an adjective and continues with a noun could be a valid candidate, or adjective noun noun could be a valid candidate, or noun preposition noun, city of San Francisco, could be a valid candidate. And this is domain independent after we have received the tagging, the labels on the unigram. So after doing that, we extract these candidates, and those are noun phrases extracted, those are adjective noun phrases, those are adjective noun noun, and those are adjective noun phrases. Those are the candidates due to the selected lexicosyntactic patterns. And then we do filtering. It depends on heuristic rules, of course. Some people say that only the longer expressions like 2 grams, 3 grams, or 4 grams could be better candidates for domain-specific terms. So they filter out these short expressions like unigrams and so on. But this is dangerous, as you may understand, because those could be regarded as broader terms, but still those are terms. Like a bridge is a term in engineering, in infrastructure. And a Golden Gate Bridge is, well, in fact, a named entity. It's a label for an instance of a class. Yep.
Necessarily think of an example, but yeah, there could be a lot of syntactic meaning in one. So maybe it's not like it's like a domain specific single noun, like
Yep.
so
Yeah, it could
like
be.
you're just eliminating
Could be.
by the number.
Could be. And this is why engineering these sets of rules for separate domains is quite a tricky story, because you have to think about all possible forks and combinations on this search space. So let's switch to statistical. Oh, what's time? Past 11. Okay, I still have some time. So rule-based, the idea for statistical family of methods is that the more frequent in use, the higher the probability it is a term. So it's a sort of a set expression. It is used frequently in many documents within this domain, and therefore the probability that it is the candidate is higher than for the expressions with the lower frequencies of occurrences. So it also says that if it's more frequent, the impact of the term is on shaping the pragmatic context within the domain is higher, because it is used by more documents written by many authors. So it better reflects the collective sentiment of the authorship within this domain. So a very simplified procedure for the statistical family of methods is you just get an n-gram from the text, and then you may wish to constrain this n to 3 or 4 or 2 or whatever, depending on the specificity of your domain. And then you count its occurrences in all the texts in the corpus. And then when you have done that, you rank the bag of the terms and get the list of the ranked terms. And then you cut off below the threshold. Good question is, what is the threshold and what is the rationale to choose the threshold? This is an example based on the same text. So these are the n-grams. Like this is a unigram, this is the b-gram, this is a 3-gram, and this is, and so on, so on, so on. And those are the frequencies. How many times this unigram has been met in this text? So, are you satisfied with such a recognition? Well, myself, I'm not, because the major part is just junk. Even if you constrain this by 3, the major part would be junk. And most frequent is junk. Like this is the unigram. And we met it 6 times. Just an article. So to improve on that, the hybrid steps in. So what people do in linguistic statistical hybrid methods, they first do linguistic and arrive at the list of noun phrases, the n-grams that are noun phrases, for instance, like here. And then you filter out all the stuff which is not, which does not satisfy the chosen lexicosyntactic patterns. And you use these candidate terms recognized by a linguistic pipeline to further apply the statistical pipeline of processing. And then you cut off at a threshold. This is the result of the linguistic step, and this is the result of the linguistic and statistical step. And still, we have a lot of non-terms here. For example, we have this stuff as named entities, and this stuff as broader terms, and only this, like most famous bridges and bridge and straight, are in domain terms. One more interesting thing is that in texts, some term candidates which are longer may contain shorter term candidates as their parts, which is called nested terms. The idea of extracting nested terms as well is to prioritize longer candidate terms as more specific, as far as we're striving for domain specificity, including those containing shorter candidate terms. So more specific terms potentially are bridge within famous bridge, bridge and gate bridge within Golden Gate Bridge. So there are methods that do nesting and nesting recognition. For example, the C-value method and our improvement of the C-value method, and the formula is over there. So this part is in fact allows us to disprioritize the shorter terms. like bridge, like gate here, by assigning longer terms containing shorter terms more rank value or more score, higher score. This is the graph-based. The idea of the graph-based family is the terms are repeated co-occurrences of unigrams, like golden gate bridge is a repeated co-occurrence of these unigrams. Golden, 54 times with gate. Just imagine a longer text and count the co-occurrences in the text. So golden, if co-occurs with gate 54 times, that is a well-repeated co-occurrence. So you have to pay attention to that. And golden, if co-occurs with bridge 38 times, this is a well-repeated co-occurrence. If you have a big corpus of documents, this will be a little bit more reliable information based on the co-occurrences in all the texts. Yeah. And this is one of the problems. So in the co-occurrence graphs, you may directly analyze only B-grams because those co-occurrences are binary. So you cannot have edges with the more arity within these co-occurrence graphs. And this could be a problem. So from here, we may judge somehow that Golden Gate is a good candidate and Golden Bridge is perhaps a good candidate and Gate Bridge is perhaps a good candidate. But unfortunately, we cannot directly judge that Golden Gate Bridge is a good candidate because it's a 3-gram. And there is no single relationship, co-occurrence relationship between those 3. So co-occurrence graphs are built using either sequential co-occurrences, like in a sequence of unigrams, Golden Gate Bridge together, or in sentence co-occurrences, like bridge and at the end of the sentence, California. Post-tagging, post-tag filtering might be applied, like here, to remove the junk just before you start building the graph, to make it less computationally intensive. And the edges are weighted by co-occurrence frequencies, terms ranked by a function of co-occurrence frequency for the vertex, and could be combined with statistical ranking for the vertices, in fact. So what is tricky in this approach is n-ary co-occurrences, which we have discussed already, corresponding to longer terms, longer than B-grams, and unigram terms in sequential. So we cannot analyze any co-occurrence for the parts of a unigram. It's a little bit easier if you use in-sentence co-occurrence, but still tricky. So this is the state of the art at 2020 in general automated term recognition on the actor dataset, which is the corpus in 3 parallel languages, English, French, and Dutch, and contains the texts in 4 different domains. And the labeled data set includes also named entities, which are labeled separately, have different labels, different from the labels of general terms. So this is the average F1 score, which is not high, as you may see. And now I believe you start understanding why it is that low. Because of the numerous questions we have asked together at the beginning of this tutorial. So the task is in fact very, very difficult, and I can't really confess that we have enough data sets to train the models on that and to experiment using even rule-based methods on those tasks. Furthermore, the understanding of what is a term in different data sets is quite different, and I will illustrate it. So, if we look closer to named entities, we may say that named entity is a word or phrase that identifies or labels or names, if you wish, a unique real-world object, like a Golden Gate Bridge. Also particular dates, the 4th of July. Also quantities, like sixpence or pound. The features of a named entity are being a proper name. Most entities are capitalized and refer to a unique object. Uniqueness, different instances of the same class normally have different named entity labels. Contextual importance, which is central to identifying who, what, and when, and where in texts. And as we already discussed implicitly, the typology of terms includes named entities as a specific kind of subclass of domain-specific terms, like Don Trump in Portos. Paralinguistic, which means informal definition of a term. So this is to take away. Golden Gate, oops, sorry. Well, no. A Golden Gate Bridge is an instance of the concept of a bridge. So this is a named entity, and this is a general term. And this is the property, which qualifies this being a named entity. Hard to recognize in a plain text because we do not have such a mapping in plain text. It's yet another question how to engineer such a mapping in a plain text, which is quite a challenging task as well. So this is for named entities. So as I have said, the number of papers is approximately 6 times more than for general term recognition. And the peak of inflated expectations is 3 years later. And the results are better. As you may see, in named entity recognition, the current leaderboard based on the, oops. Sorry. The current leaderboard based on the CoNLL dataset, which is English, for the last 10 years is, as you see in the table, with the champion having F1 score of almost 95%, which is great. And this is an LSTM plus a transformer. So here, the neural networks start working much better. Large language models like transformers start working better because of several reasons. And these reasons are well, I will show it in one of the subsequent slides. So this is our recent development called ExtractMat. together with Dmytro Chaplinsky and some master students. So in terms of the methods, it's a hybrid thing, which is rule-based, linguistic plus statistical. It allows doing nested recognition based on C-value. It allows using sentence embeddings, using a re-rank approach, and it is multilingual. At the moment, it does for English, German, Ukrainian, French, and Dutch, 5 European languages. So I believe that Dmytro will tell you a bit more about this software, which is publicly available as a GitHub repository in his part of the tutorial. And this is the data set we used for initial testing of Extractomat. It is trilingual. It is English, German, and Ukrainian, parallel corpora. German and Ukrainian translations have been done by native speakers and experts in the domain. And the domain was knowledge representations of time. The title of this paper is Ontology of Time, Review and Trends. It's a research paper. It's a survey paper, in fact. Written about 10 years ago, 10 plus years ago. We have the authors of this paper in the team developing Extractomat. So the markup, I mean, the original English term markup in the paper has been done by one of the authors. So a person who is knowledgeable about what he has written. So it is small because this is not a real data set for doing some cross-evaluation. It's more about initial feasibility testing of the software to check if it does work correctly and to get some indicators of its performance. So the terms counts are for English 272, for German the same, and for Ukrainian slightly more, 289. So which is comparable. So the data set is really parallel. This is the translation of the same paper. And the markup, well, very much resembles what has been done in English. This is for German, and the same for Ukrainian. It took us some time to do this trilingual thing, but this was the reward. Extractomat on this very small indicative data set worked quite well. So for English, that was the F1 score, which is much better than the previous leaderboard I have demonstrated, though it could not be directly compared because the data sets are different. And as you may see, it behaves roughly similarly for different languages. So we can say that the approach we have taken is, so to say, language independent up to the part of speech tagger used, because we used 3 different or 5 different part of speech taggers for each language we are capable to process. And this is our next experiment, just to compare directly Extractomat with the rest on the leaderboard on Actor of 2020. So as you may see here by the values, it is not astonishing. And this is the place in the leaderboard Extractomat occupies based on the values which we have obtained in the experiment. You might wish to ask, what are the reasons of such a serious drop in performance? Any intuition on that? just to recall. This is on OTRT, where we have also English. And this is for Octar, where English is one of the languages. So we may compare using the English overlay. But we also added French and Dutch post taggers. So we processed French and Dutch parts of the corpus as well. No idea? Yep. Well, it differently works for different languages, as you may see, and it depends on the quality of post tagging. Most seriously, there are some other dependencies. We are not fully sure that. So we have to check the code in order to find out if those numbers have been computed correctly. But I'm quite sure this is the pessimistic view on the performance. So these are the performance diagrams. This is for the OTRT dataset, and this is for the actor dataset. And the method used was re-rank. So as you may see here, F1 score is a blue curve. The maximal value for OTRT is around 0.8, and the maximal value here is 0.24 for English, times lower. And these are two reasons which we have identified. The post patterns, linguistic patterns we mentioned for the linguistic methods were developed, the set of rules, in the view of OTRT labels. So we didn't check or change these lexicosyntactic pattern rules for selecting candidates after we have experimented with OTRT. Perhaps Octar understands what is a candidate term and what is not a candidate term slightly differently as we did while marking up OTRT. So this is one of the challenges in the domain, by the way. So if you take two different data sets, you cannot directly compare the results, just because if you have 4 experts labeling the data set, you will have 6 different opinions. So, and the second, the understanding of what a term is different in OTRT and actor as well. So if we compare named entity recognition with the general automated terminology recognition, we could observe that named entities are named instances of entity types versus named entity types and instances in terms in general. Named entity recognition has more consensus in a definition what is a named entity, and the notion of a named entity is easier to grasp and comprehend and formalize. There are more data sets and for named entity recognition tasks. It's a little bit more practically demanding set of downstream tasks beyond named entity recognition. So hence, the state of the art, the performance is better. And for terms in general, we have less consensus in definition. It's harder to recognize terms or not terms. There are less data sets. There are many different opinions on what is a term. There are less solutions to complete the task, and even more downstream tasks for general automated term recognition, including those for the named entity recognition, by the way. The consequence is that the state-of-the-art performance is worse substantially times. So what could be an immediate conclusion after this comparison? In my opinion, it just says that we have more opportunities to gain impact with the general automated term recognition. So focus on that. Do not do named entity recognition. Many people have already done it quite well. So continue in this more complex and general setting. And these are the research challenges, quite a list. I will not use your time for reading the list. I will just 5 minutes. Okay, you see? I'm not allowed to read this list and discuss this list. I will just say that the slides will be available and you will have plenty of chances to read this down by yourselves. And even more, ask Dmitra. He is also informed by the challenge, about the challenges a little bit. Yes. So, what I can say at this slide number 42, there is no a universal answer to all this set of challenges. So you have to elaborate it one by one and choose the proper focus. Let's look slightly beyond, quickly, 5 minutes. Let's look at the available definition of what is a term. I've ordered them chronologically, and perhaps one of the first came in 1979, Rister, saying that a term is a concept reference system within a specialized field. So pointing to semantics. In 1990, Sagar wrote that a term is a surface representation of a specific domain concept, pointing to semantics. Kagiura and Umina in 1996 said that term equals to word or phrase related to domain-specific concepts, which encompasses termhood. Very similar to the previous two. There is an outlier here, which is more linguistic. Justerson and Kurtz in 1995 wrote that terms are domain-specific noun phrases identified by pause patterns and statistical scores. They were the early advocates of rule-based hybrid methods. So this is a little bit more operational definition, pointing to the methods. So, and this is the standard. ISO 1087-1 says that a term is a verbal designation of a general concept in a specific field, which is vague and implicit again. One of the recent definitions, Saint Martin in 2022, just 3 years ago, he wrote, the terms do not carry meaning in themselves. Clear? They're access points to large repositories of knowledge. For example, their semantic potential. So yeah, terms are just the doors, the gateways to the knowledge formally represented. Six out of 7 just say, let's make semantics great again. Looks like MAGA, and this is why this is a potentially great research direction. But let us see if those definitions are correct and on what. Let us understand if they agree and on what. For me, it's quite a simple thing to do because I have already highlighted the degree of their consensus, just one outlier. The greenish one. But all of them fail to offer how to follow to go into this potentially great research direction. I will try to hint you. By recalling this picture about the place of a term in a language and the typology of terms. A term is a word or expression that has a precise meaning in some uses or is peculiar to a science, art, profession, or subject. This is the current state of the art. I mean, those two diagrams. And this is the challenge. The difference between a term and not a term is tacit and blurred. The difference between the kinds of terms is also tacit and blurred. And this is the way to attack the challenge. Just buy a hat and change the letter. You have to expand and refine formal semantic specification like here to make the overlapping between the formal science system and terminology broader. And then it may reward you. So you may do this by reducing the impedance mismatch between tacit lexical and formal semantic representations and build what we call lexico-semantic bridges. For example, starting with a word net and going through ontologies and RAG and knowledge graphs, exploiting the chains of thought. And finally arrive at something that adheres to St. Martin's definition, a gateway to the semantic world. There are more hints how rule-based methods could be improved. So first you have to better understand or specify what a term is and come up with a consensual definition in the community just to align the data sets in those meanings. And then you have to improve, you may wish to improve recall by text expansion. For example, if you look here, this "it" is also the Golden Gate Bridge. And this is also the Golden Gate Bridge. So why not making it explicit in the text by replicating Golden Gate Bridge here and here? This is a very trivial thing, as it could be seen by a human, but it's not that trivial for recognizing this pots of sentences for expansion for a machine. So it could be a nice topic to research into. What else could be done? You may wish to resolve tree-like mentions, like if you look here, this is a part of a sentence in our OTRT dataset based on having an adequately rich and deep model of time. If we go through the pause labels, we can extract model, time, model of time, deep model of time, rich and deep model of time, adequately rich and deep model of time. If we look at what the phrase means, it means that there is a model of time which could be qualified like a deep model of time and rich model of time as a separate branch on the fork, and those further on are adequately deep and adequately rich. Some parts of this are missing in what we have extracted before, just because we have a fork, an implicit fork in the phrase, in the text. So we may apply text expansion here as well. For example, you may add the fragments and make this tree-like mention explicit in the text. And then you get a better coverage and better recall for your method here. And by the way, the stuff that you have already identified or recognized using the pause-based approach and which didn't appear here could be retained from here, from the previous step. And then you increase your recall even more. So, and finally, this is a very, very simple idea about how to distinguish between domain-specific and interdomain term candidates. So imagine that you have a list of term candidates. What you may wish to do is to take a different text corpus from a very different domain, extract the terms in there, and then compare the lists. If this is true, then you will have a lot of term candidates that are met only in one of those domains. So presumably they are good candidates for domain-specific terms. And if you meet things in both domains, in both data corpora, then it could be regarded like common terms, if those are terms. For example, yeah. Physics and mathematics are good examples because those have an overlap. For example, time could be almost equally frequently met in both physics and mathematics. And this is the problem. So as I have written in the bottom of this slide, the problem is how to ensure that the domains are not overlapping. So you have to very carefully select the corpus for a different domain to somehow ensure that the terminological footprints are different. So a way to go is to be inventively hybrid and benefit on synergies between different families and different methods in order to get more reliable and better performing results. So, and now I'm going just to announce the practical part, Dmitry with his subsequent tutorial, and this is his motto. It says, in theory, there is no difference between theory and practice, but in practice there is. So by that, we're entering the dangerous area of 51 to practice in there. This is the line. Yeah, thank you for being patient, and I'm happy to take your final questions whenever you wish, even during the lunch. Thank you very much.